A blockchain or Bitcoin would be complete without understanding the Merkle tree. This is an underlying fundamental technology on how this whole thing works. So basically a Merkle tree is a hash tree, or a Merkle tree is a tree in which every leaf node is enabled with a cryptographic hash or block. So that is blockchain, and it's in a nutshell. So every node, not a leaf, branch, internodes, inodes, labeled with that cryptographic hash and the labels of its child nodes. So these things can grow in really weird ways. And that's the whole idea from the Genesis block on forward, is that you actually have a hash tree. And that hash tree is what we're mining, and that hash tree is what we're shoving into the data for this in terms of how the entire process works. That top hash is your Genesis block, then block 0, block 1, and then the combinations thereof. And it just keeps on going down the street until you reach the end of it. And wherever that end is may never happen. So really good example, and if someone asked me where I got this from, I got all the images from Wikipedia. All right, so what are they used for? So hash trees can be used to verify any kind of data that's stored, handled, or transferred in between computers. And again, we're utilizing our peer-to-peer network, we're doing hash trees, we're doing hash bits. It will work all the way across the board to make sure that the data you get is undamaged and unaltered. It can even check what other peers don't lie and send fake blocks. And that's exactly why the people that invented Bitcoin chose this, is because it has all this inbuilt cross-checking and verification. Hash trees are used in other systems and in other ways. DAT pools, Apache Wave protocols, Git, Mercurial. It's used as part of hard drive operating systems, ZFS file systems. So it's really used a lot. It's really neat in terms of how this is used beyond just Bitcoin, Ethereum, and all the rest of it. There's a whole bunch of other things that are using it. The Certificate Transparency Framework, Nix packages, GNU Guix, NoSQL, Apache Cassandra. Again, this is a real basic technology. This is used by a lot of systems, not just Bitcoin or blockchain. Now, the initial Bitcoin implementation of Merkle trees by Satoshi applies to the compression step of the hash function to an excessive degree, which is mitigated by using fast Merkle trees. So there's ways of combining this in your computer science to make this a whole lot more cool in terms of how that works. So how this is used in blockchain is you have various blocks, previous hash, timestamp, nonce, and all those hashes and all the rest of it that goes into the process for it. So previous hash, nonce, goes to previous hash, goes to nonce. And again, that whole process, we're stringing these things together as part of that tree to make sure of what we've got and make sure the data is good in terms of what we want to have inside that data block. So the blockchain, a growing list of records called blocks, they're linked together cryptographically. And that's the good part. Each block contains a cryptographic hash of the previous block, a timestamp, and then the transaction data. And again, remember, our size of our block is limited to 1 megabit. So that transaction data is what we're going to be working with. But that blockchain, generally represented as a Merkle tree, is where we're going to format all this stuff out. So we have all of those peer-to-peer and processes, and we have all that cross-check validation. The timestamp proves that transaction data existed when the block was published. Blocks contain information about the block previous to it as they form a chain, with each additional block reinforcing the ones before it, again, which makes it harder to lie about what the block is and the data that's in it, because remember, we're hashing all that stuff. So blockchains are resilient to modification of their data because once recorded, the data in any given block cannot be altered without altering all subsequent blocks. And this can cause a problem with some of the uses inside of how we're looking at blockchain, especially in things like education, especially things in like where the data may be derogatory, credit ratings and things like that. So sometimes that's not necessarily a good thing, but it's how it's worked. P2P network of data. Blockchains are typically managed by a peer-to-peer network for use as a publicly distributed ledger, where nodes collectively adhere to the protocol to communicate and validate new blocks. Again, we pulled this into a number of miners. They're basically our gateway. And even though blockchain records are not unalterable, forks are possible. That's the other part about this. And you can literally fork something. And there's something called what's called the high Byzantine fault tolerance. And this is actually really cool, right? So if the Byzantine fault tolerance is a really cool way of looking at how data is done. And the P2P network really does take a look at this. In its simplest form, and I pulled this off the web, a number of generals are attacking a fortress and must decide as a group only whether to attack or retreat. Some generals may prefer to attack while others prefer to retreat. So the important thing is that all generals agree on a common decision, for a half-hearted attack by few would become a rout and is worse. So basically that Byzantine fault tolerance is that everyone has to agree or no one agrees. You can't have a couple of systems go their own way and say this is good or say this is bad without everyone agreeing. And that's what they mean by Byzantine fault tolerance. So you're going to hear this inside of the network, especially as you get down into the coding side of it. But again, the idea is just think about it as generals attacking a fortress, and that all the generals have to agree to the attack. Otherwise, it won't go down. It would be ugly. So that's where it works. So used in Bitcoin. The Merkle tree is useful because it allows users to verify that specific transaction without downloading the whole blockchain. And again, right now it's over 350 gigabytes at the end of June 2021. That's the last side I could get in terms of how this works. For example, say you wanted to verify that a transaction HD is included in the block. You have the root hash that goes along with that, and you can query the network about HD, and it will return a bunch of other things along the way. Right? The Merkle tree allows you to verify that everything is accounted for with these hashes, given HAB, HC, HEFGH, and the root HD is only missing hash has to be present in the data, and that is the big key on this, right? We're verifying the data. The Merkle root, a simple mathematical way to verify the data in a Merkle tree. Merkle roots are used in cryptocurrency to make sure data blocks passed between peers on a peer-to-peer network are whole, undamaged, and unaltered. Right, and again, they're central to the computation required to maintain cryptocurrencies like Bitcoin and Ethereum. And that's the other big important part on this one. It's a big part of the validation process. So blockchain data. Blockchain, as we've been learning, again, composed of various blocks that are linked to one another, hence the name blockchain. The hash tree, the Merkle tree, encodes the blockchain data in an efficient and secure manner. Now, we do put checks in there. We do say that there's a limitation on size of 1 megabit. We do try to have a level of difficulty where each block works out to be a computational movement of 10 minutes. So you can do this in such a way that we can either do this quick or slow, and there are quick movements of large data around one computer node to another on the blockchain network because of the way that the hashing works, and the Merkle tree allows you to move along that tree, right? Every transaction occurring on the blockchain network has a hash associated with it, and so basically you're just looking for the hash, and that is something that computers are really good at. Pattern matching, really good, especially in text level. So it's going to work really, really quickly when we're trying to pull the data up if we've set our query parameters correctly. So numerous transactions are stored on the block though, so we not only need to know the block hash, but we need to know the transaction hashes in the block, right? So example, 7 transaction block, the lowest level, got the leaf, would be 4 transaction hashes. And as we kind of move through that, we're going to see how all those hashes connect to each other. So there will be one last transaction hash called the root, and it will connect to the 2 hashes below it at level 1. So there's a lot of things that go along with that hashing process. Again, lots of math here. So this may not be your thing, but just understand that there are numerous transactions stored in the block, and that all the transaction hashes in the block are also hashed. Right? The verification process, enter the root, which further speeds up verification, since it carries all the information about the entire tree, and one only needs to verify the transaction hash and then keeps on going. Essentially, the Merkle tree and the Merkle root significantly reduce the levels of hashing to be performed and enabling faster verification and transactions. Again, remember, computers are really good at this. Pattern matching, really good at it. So that's where this is going to go. So fitting all this stuff into the block is a place in the blockchain where the information is stored and encrypted. Right? So we do have our hashing and all the rest of it. Blocks are identified by long numbers that are hashed that include encrypted transaction info from previous blocks and new transaction info. Blocks and the information with them must be verified by the P2P network before new blocks can be created. And then blocks and blockchains are not solely used by cryptocurrencies, and we'll go over that later on as we go through and we see the other uses for the block and the blockchain technology. It's really interesting how other groups like education and contracting and shipping and supplies are actually using this technology to do other things. So again, Merkle tree is basically cryptography and computer science. It's a hash tree on which every leaf node is labeled with a cryptographic hash of block data. And that's really all it is. It's what you kind of need to know for this level of information. You don't need to understand how it's computed or anything else. But again, you just really should know that it's a way of traversing all of the different blocks to try to find the transaction that you're looking for. And that it's a really efficient way of doing it once the block has been created. Block creation is a whole other subject. But again, that's essentially what a Merkle tree is. I hope you enjoyed this lecture, and I hope you will see me in the next one.